Hello students, very good morning. Today we are going to talk about the next topic, that is Henry's Law. In the previous video, I discussed that when gas is compressed over the liquid at a very high pressure, more molecules will get dissolved and the solubility increase, isn't it? So in order to explain this effect of pressure on the solubility of gas, Henry, he said something, he stated a law, he gave a law. So before getting into the topic, let's understand what is partial pressure. Now, partial pressure is the pressure that is exerted by a gas in a mixture of gases if it occupied the same volume as the mixture at the same temperature. Let's take, if we have taken more than one gas, just say we have taken oxygen, nitrogen, hydrogen, okay? If we take more than one gas, then we would consider the partial pressure of the gases, okay? If we have the partial pressure, now if we have oxygen, nitrogen and hydrogen, the solubility, it depends on their partial pressures, okay? So for example, if we have this nitrogen gas only, all right, now how much nitrogen will get dissolved, it depends on the partial pressure of nitrogen, all right. So Henry's law, Henry stated that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas which is present above the surface of the liquid, okay. So he said that the solubility of a gas in a liquid, solubility of a gas in a liquid is directly proportional to the partial pressure of the gas, okay, partial pressure of the gas which is present above the surface of the liquid. Now Dalton, he was a contemporary of Henry, and he independently concluded that if we use the mole fraction of a gas in the solution as a measure of its solubility, then according to him, the mole fraction of gas, mole fraction which is denoted by this zeta, mole fraction of gas in a liquid is directly proportional to the partial pressure of the gas, okay. So greater the mole fraction of a particular gas inside the liquid, more will be the partial pressure of the gas, isn't it? More will be the partial pressure of the gas on the surface of the liquid. So solubility in that case, it increases, all right. So, or you can say it like this also, that if we can say that the partial pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in the solution, all right. So to remove this proportionality sign, we have introduced a constant which is known as Kh, or Henry's constant, okay. This is Henry's law constant or Henry's constant. So according to Dalton and according to Henry, the partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas, okay. So this was all about the Henry's law. Now let's have a graphical representation, okay. So now we just see, we have saw this, that P is equal to Kh into zeta, all right. This is the mole fraction. Now how do we calculate this Kh? Now different gases, they have different values of Kh at the same temperature, which suggests that Kh is a function of the nature of the gas, all right. So how Kh is calculated? Different experiments were done, and some scientists, they plotted graph. One experimental result was seen for the solubility of HCl gas in cyclohexane at 293 Kelvin. So let me draw this graph. So this graph is the experimental result for the solubility of HCl gas in cyclohexane at 293 Kelvin. You can see this, that a straight line has been obtained. Okay, after calculating the slope, all right, after getting the slope, it was found out that P by mole fraction of gas is equal to KH. Okay, so the slope of this line is the Henry's law constant KH, which is equal to the partial pressure upon the mole fraction. All right, so KH, it is dependent on the nature of gas. It depends on nature of gas or nature of solvent. Fine. So this is so. Different gases have different KH values, as I explained earlier, that different gases, they have different KH values at the same temperature, which suggests that KH is a function of the nature of the gas. All right. Now, for example, let's see here. For example, the KH for different gases in water, KH for different gases in water at 20 degrees centigrade or Celsius is given. So KH in kilobar we will take, and the gases. So in this, first let's take helium, then hydrogen, then oxygen, and you have seen here that approximately the values lies like this. Fine. Now if we change the solvent, we have taken the solvent as water, isn't it? But if we change the solvent or change the temperature, the KH for these particular gases will also change. Okay, so now you have we have seen this combination, this relation, and we can write it like this also. In liquid, mole fraction of gas in liquid is equal to P by KH. Okay, so now just see here that if the value of KH is greater, okay, the mole fraction of gas also decreases and the solubility also decreases. Fine. This is because there is an inverse relationship between the KH and the mole fraction of the gas. Okay, so if we see the solubility, if we want to know the solubility of all the three gases which is written over here, and you have to find out that which one is more soluble and which one is less soluble. So if the value of KH is more, if the value of KH is more, see here, if the value of KH is more, the mole fraction must be less, because the inverse relationship is there, so the solubility will be less. So here we can see the value, we have taken it in kilobar. Okay, the value of this helium is 140 approximately, so we can say that it is nearly insoluble. Okay, now next just see hydrogen. The value of KH is less than helium, but here also we can say that okay, it is soluble, it can be soluble as compared to this. And oxygen, here the value of KH is very low. If the value of KH is low, the mole fraction of the gas increases and the solubility also increases. So that is why the oxygen, it has very good solubility. It is highly soluble, not just soluble, highly soluble. Alright, so this is how the solubility is dependent on the mole fraction, and the value of KH there is an inverse relationship between the value of KH and the mole fraction of the gas. Now let's see that how temperature affects the solubility. How temperature affects the solubility. If you increase the temperature, the value of KH also increases. Okay, and so if you increase the value of KH, what happens? The mole fraction of gas decreases and the solubility of gas decreases. So this is because this is due to this reason that aquatic species, they are more comfortable in cold water rather than in warm water, because in cold water the temperature is low. If the temperature is low, the value of KH is what? It is also low. If the value of KH is low, the solubility, or you can say the mole fraction of the gas, is high, and the solubility also is high. So more gases like oxygen, nitrogen, it is more dissolved in cold water. Now a question is there. At same temperature, hydrogen is more soluble in water than helium. Okay, so which of them has higher value of KH and why? This is a very good question, that at same temperature hydrogen is more soluble in water than helium. Which one of them has higher value of KH and why? So this is because just in the previous example you must have seen that the value of helium was 140 and that of hydrogen was 75. So helium, it has a higher value of KH. If it has a higher value of KH, all right. So if the gas has higher value of KH, it means that it is less soluble, and as hydrogen has lower value of KH, it is more soluble. Okay, so that is why hydrogen is more soluble in water, because the value of KH is low, and that of helium, the value of KH must be high, so that is why its solubility is low. So what are the applications of these Henry's law? So first is in the production of, if we talk about the application, first is the production of carbonated beverages. So to increase the solubility of carbon dioxide in soft drinks and in soda water, the bottle is sealed under high pressure. Okay, so this is the first application. Second application is in deep sea diving. In deep sea diving, what happens? The scuba divers, or you can say the deep sea divers, they breathe air at very high pressure underwater. So increased pressure, it increases the solubility of atmospheric gases like nitrogen in blood. So when divers, they come towards the surface, the pressure gradually decreases, resulting in the release of dissolved gases from the blood, which leads to the formation of bubbles of nitrogen in the blood, which tends to block the blood capillaries, and it rises an ailment called bends or decompression sickness. To avoid bends as well as the toxic effects of high concentration of nitrogen in blood, the scuba divers, they carry a tank which is filled with air diluted with helium 11.7%, then nitrogen 56.2%, and oxygen 32.1%. Okay, after this, this is also applicable for people living at high altitudes, or you can say the climbers who climbs mountains and so. So at high altitudes, what happens? The partial pressure of oxygen is less than that at the ground level. So this leads to low concentration of oxygen in the blood and tissues of people living at high altitudes or climbers. So they feel weak both physically and mentally. So these are the conditions of some medical condition known as anoxia. So these were the applications of Henry's law, and this was all about Henry's law. So that's all for today's video, students. Thank you so much. Have a great day.